Section: Introduction. We're seeing a growing need to train large models with long sequences in various fields, from AI that can generate content to models used for scientific discovery. In the realm of AI, tasks like conversational AI, summarizing long documents, and generating videos require the ability to reason over long contexts in both spatial and temporal domains. For instance, multimodal foundation models, which process speech, images, and waveforms at the same time, need to reason over high-dimensional inputs with extremely large sequences. Similarly, summarizing entire chapters or books, which can contain tens or hundreds of thousands of words, is crucial in conversational AI and abstractive summarization tasks. Long sequence length is also vital for AI and scientific fields, helping us better understand structural biology, healthcare, climate and weather forecasting, and large molecular simulations. For example, we can adapt large language models with gene sequences to create models that can learn the evolutionary patterns of genomes using simple alphabets and extremely long sequences. In healthcare, predictive models for diagnosis that are conditioned on a patient's entire care record require the context of long sequences. Despite the growing importance of long sequence length for both generative AI and AI for science, current large model training systems and the parallelism technologies they use, data, tensor, pipeline, sequence parallelism, struggle to efficiently support long sequence training. Two main challenges arise with the current parallelism approach. First, it can't scale along the sequence dimension. Second, existing sequence parallelism approaches are inefficient due to memory communication inefficiencies. Moreover, current approaches are difficult to use, requiring complex and error-prone code refactoring. In this paper, we present DeepSpeed Ulysses, a simple, portable, and effective method for enabling highly efficient and scalable training of large language models, LLMs, with extremely long sequence lengths. DeepSpeed Ulysses divides individual samples along the sequence dimension among participating GPUs. Then, right before the attention computation, it uses all-to-all communication on the partition queries, keys, and values so that each GPU receives the full sequence but only for a non-overlapping subset of the attention heads. This allows the GPUs to compute attention for different attention heads in parallel. Finally, DeepSpeed Ulysses uses another all-to-all to gather the results along the attention heads while repartitioning along the sequence dimension. DeepSpeed Ulysses offers several contributions to advance the state-of-the-art in long sequence parallelism. 1. It trains transformer models with sequence lengths 4 times larger than existing systems, enabling training with sequences with over 1 million tokens. 2. It reduces communication by over 10 times compared to existing systems, resulting in throughput improvements of up to 2.5 times, and sustained throughput of over 175 trillion floating-point operations per second, TFLOPS, per GPU, which is over 54% of the hardware peak. 3. It supports dense as well as sparse attention, and it works with efficient attention implementations such as Flash Attention version 2. 4. It works together with 0.3 to support not only large sequence lengths but also massive model sizes. 5. It's easy to use and portable, requiring minimal code changes to the existing training frameworks. In the following sections, we'll provide background and related work, a detailed discussion of DeepSpeed sequence parallelism core design, communication complexity analysis, experimental evaluation, and comparison with existing work. The transformer architecture is a key part of this discussion. It consists of input sequences projected into queries, Q, keys, K, and values, V, embeddings. These are typically a 3D tensor of size n, b, d, where n is sequence length, b is micro-batch size, and d is hidden dimension. The QKV tensors are fed to the attention block, a central component of the transformer model. Outputs of attentions are inputs to the multi-layer perceptron, MLP, block of the transformer architecture. The attention block followed by the MLP block are replicated multiple times to form an encoder, a decoder, or an encoder-decoder transformer network. Data parallelism is a common method of accelerating neural network training and has been widely applied with different neural network architectures and applications. However, it is limited when the model is large and model parameter replication across devices is practically infeasible. Zero optimization addresses this problem by partitioning model parameters across available compute devices. Tensor and pipeline parallelism are two other popular methods for large-scale training. Our proposed approach, DeepSpeed Ulysses, can be used with both methods. By leveraging sequence parallelism to keep the global batch size at a reasonable size on large systems, we effectively reduce the impact of large batch size on model quality. Section Summary. Training large models with long sequences is crucial for generative AI and AI for science, but existing parallelism approaches are limited in their ability to support efficient long sequence training. In this paper, the authors introduce DeepSpeed Ulysses, a methodology that enables highly efficient and scalable training with extremely long sequence lengths. DeepSpeed Ulysses partitions individual samples along the sequence dimension among participating GPUs, employs all-to-all communication collective for attention computation, and supports dense as well as sparse attention. It achieves 4x larger sequence lengths, reduces communication by over 10x, and supports massive model training with minimal code changes. Section. Related work. Let's delve into the existing research and methods related to distributed training for deep neural networks. There are two main categories: data and model parallelism. However, these methods have limitations when it comes to handling the memory overhead associated with extremely long sequences. Recent developments in sequence parallelism have attempted to address this issue, but they often fall short in terms of communication efficiency, which limits their scalability. In sequence parallelism, the input data is divided along the sequence dimension. However, different methods vary in how they partition input projections and how these partitions are aggregated and communicated for attention computation. For instance, one method uses a ring-like communication collective, where query projections are local, and key and value projections are transmitted in a ring style to compute global attention. This results in communication complexity that increases linearly with the size of the message. Another approach, known as Megatron-LM sequence parallelism, is closely integrated with Megatron tensor parallelism. This method also partitions the sequence along sequence dimensions and uses a combination of all gather and reduce scatter collective to aggregate QKV projections for attention computation. However, unlike our approach, the communication volume in Megatron-LM increases linearly with the message size, regardless of the number of compute devices. There are also other related works focusing on full attention approximation, such as sparse attention, and single GPU memory and compute-efficient attention, like flash attention. These methods are not directly related to our work but have been used as references. Now, let's look at the core design of our system, DeepSpeed Ulysses. It follows the known transformer architecture, where input sequences are divided across available devices. Each local partition is projected into queries, Q, keys, K, and values, V, embeddings. These embeddings are then gathered into global QKV through highly optimized all-to-all collectives between participating compute devices. After this, attention computation is performed, followed by another all-to-all collective that transforms the output context tensor of attention computation to sequence parallel for subsequent operators in the remaining modules of the transformer layer block. What sets DeepSpeed Ulysses apart from other long sequence approaches is its smaller aggregate communication volume and better scalability with increasing degree of sequence parallelism. In modern clusters with intranode NV switch interconnect and internode fat tree IB topology, the communication volume transmitted per link for an all-to-all for aggregate message of size M over P GPUs is MP. Therefore, DeepSpeed sequence parallelism incurs an aggregate communication volume per link of 4 nhp, which remains constant when both n and p are increased proportionally. In contrast, existing approaches like Megatron-LM incur communication volume that increases linearly with n regardless of p, while DeepSpeed sequence parallelism reduces the activation memory when training with longer sequences. It does not impact the memory consumed by the model states. To support large sequence length training with large language model, DeepSpeed sequence parallelism is integrated with 0.3, a memory optimization technique for training large models. Unlike the classic data parallel training of neural networks where model states are replicated across data parallel ranks, 0.3 optimizes memory usage by partitioning model states across data parallel ranks. In DeepSpeed sequence parallelism, 0 partitions model states across both sequence and data parallel group and collects per rank partitions when they are needed. This allows for significant memory savings and enables scaling not just to large sequence lengths but also to large models. Section Summary. DeepSpeed Ulysses is a sequence parallelism approach for training large language models that addresses the memory overhead and communication efficiency limitations of existing methods. It introduces ring self-attention, a communication collective that partitions input data along the sequence dimension and computes global attention with linear communication complexity. Compared to other approaches like Megatron LM, DeepSpeed Ulysses achieves better scalability and significantly higher training efficiency with extremely long sequences. Additionally, DeepSpeed sequence parallelism is integrated with 0-3, a memory optimization technique, to support training with large language models by partitioning model states across both sequence and data parallel groups. Section. General and attention-agnostic solution. We've developed a versatile solution called DeepSpeed Ulysses, which can handle any type of attention, such as self-attention, cross-attention, and causal attention. This includes both dense and sparse versions, as well as optimized kernels that support long sequences at the local attention level, like different versions of flash attention. The versatility of DeepSpeed Ulysses comes from its core design, which is centered around attention and sequence parallelism. Before the attention computation, there's a sequence parallelism of NP partition. The attention computation involves head parallelism with full attention per head, but with fewer heads. This means that the attention computation can be replaced with any type of attention mechanisms, such as dense attention and various forms of sparse attention. We tested DeepSpeed Ulysses on GPT and BERT, which are foundational models for many natural language processing tasks, using up to 64A100 GPS. Our tests focused on 4 areas: sequence length scalability, throughput for dense attention and comparison with existing systems, throughput with sparse attention and comparison with existing systems, and a convergence study of deep sequence parallelism. In our first set of experiments, we tested the strong scaling of sequence length up to 1 million tokens on a GPT model with 1.2 billion parameters. The results showed that DeepSpeed sequence parallelism allows the sequence length to increase linearly with the number of GPUs. It also maintains a similar computation throughput across different sequence lengths at the appropriate GPU count. Next, we tested DeepSpeed sequence parallelism on a dense attention model with 30 billion parameters and compared it to Megatron sequence parallelism on 64A100 GPS. Our results showed that DeepSpeed sequence parallelism consistently outperforms Megatron LM for the sequence length that can be run with both. Moreover, DeepSpeed sequence parallelism can run longer sequences than Megatron LM. The performance advantages of DeepSpeed sequence parallelism are twofold. It fits more samples than Megatron LM due to memory optimization, leading to higher throughput, and it benefits from efficient all-to-all communication relative to all-gather communication as applied in Megatron LM sequence parallelism. We also tested DeepSpeed sequence parallelism on a sparse attention model with 30 billion parameters and compared it to Megatron sequence parallelism. The results were similar to the dense attention experiments. DeepSpeed sequence parallelism outperformed Megatron LM for the sequence length that can be run with both. In fact, the current DeepSpeed throughput is bottlenecked by the local sparse attention implementation, and as a result, DeepSpeed throughput decreases as the sequence length increases. We expect this performance gap between DeepSpeed and Megatron to increase further for larger sequence lengths as we improve the performance of the local sparse attention implementation in the future. Finally, we conducted a convergence study of a GPT model with 1.3 billion parameters at a 32K sequence length on 8A100 GPUs with a sequence parallelism degree set at 4 for both DeepSpeed and Megatron LM sequence parallelism. DeepSpeed sequence parallelism is a purely system optimization technique that enables the training of long sequence transformer models, and it doesn't negatively impact the quality of trained models. This was confirmed through our experiments.